All right, I'm going to provide you with this video explanation of these problems to help you process these concepts one more time before the mini check. Now, to convert from a rational exponent to a radical expression, it's this idea of flower power. Remember that the top is the power and the bottom is the root. So our goal here is to write this as a radical. And really, you're just putting the number 2 where it's supposed to go. That's the power. And you're putting the 3 as the root. That's it. That's your final answer, unless you had decided to write the power on the outside. You can do that. In other words, you can see the square out here, and it would be the same thing. So 1/4, well, 1 is the power, 4 is the root, but really it's understanding that we're writing this as some type of radical. So it's definitely going to be a radical of xy, and the only thing to make this right is to put a 4 right here. Really don't need to see the 1 because a power of 1, of course, is not going to change anything in this problem. So you can leave that out. We have the 4th root of xy. Now for this problem, what we want to understand is that the exponent is by default only applied to the x. Now the reason that that's the case is because exponents always apply to what is immediately beside them. Had there been parentheses like this, then the exponent would apply to the 2 also. So what's happening here is that the only thing that goes under the radical is going to be the x, and of course we still adjust and place the power on the as the exponent, and we put the 5, the root, here for the radical. But the 2 is on the outside, so we have 2, the 5th root of x to the 3rd. So what if we go the other direction? If we go the other direction, it's understanding that we're trying to write it as an exponent. Now, in this case, the only thing that has the exponent is going to be this xy, because that's the only thing that's under the radical. So that means it's got to be xy to some power. Well, the some power is going to be a power of 3, but of course an assumed root of 2, so an assumed denominator of 2. So we have xy to the 3/2 power. What about that 6 that was out front? Well, it's just out front of this xy to the 3/2 power. How'd you do with this one? Really no tricks. I hope that you just put it as 3, x to the 3/5 power, x to the 3/5. Problem like this, it is helpful to realize this is a square root, so it's assumed to be a 2. The xy squared is what is going to be raised to this exponent. Remember, the exponent on this problem is assumed to be 1. Notice that the 2 I have only put on the y. That is a little tricky, but the 2 is only on the y. So that means that it's xy squared, the whole thing, to the 1/2 power. Okay, the 2 I was referring to was this 2, which again is only on the y. Now, if you wanted to, you could bring this exponent in. Why would I bring this exponent in? Honestly, because it cancels with the y squared. Since it cancels with the y squared, I can kind of get a little less written for my final answer. But what I had originally up here would be fine. Again, xy squared to the 1/2 power. All right, we get into some ideas with radicals that we've been working on, where you're trying to take out a some type of perfect number that's inside of 40. Now you got to know your cube roots. Cube roots would be like numbers like, perfect cubes would be numbers like 1, 8. Then it bumps up to 27, up to 64. Now, where are these numbers coming from? Remember, this is the same as 1 cubed. This is the same as 2 cubed. 27 is the same as 3 cubed. 64 is the same as 4 cubed. So I'm looking for numbers like 1, 8, 27, or 64 that's inside of 40. And the number that you get at is the number 8. 8 is able to come out. The whole thing comes out. It turns into its root. That means it turns into a 2. but it leaves behind the root 5. So we have 2, the cube root of 5. Okay, now this is a square root. Why is it a square root? Well, because it's what happens when you don't see that root written. It's assumed to be a 2. So now we're thinking of numbers that are perfect squares. Numbers that are perfect squares, you've seen them many times. Numbers like 1, 4, 9, 16, 25, 36. So these numbers all come from squaring a number. Now, as I gave you a hint in this problem, why not think about taking out 100? Now it's 100 times 3, but you're really taking out 100 because 100 is a perfect square. Now when it comes out, it turns into a 2. That's because you do the square root of 100. So we get 2, and then it leaves behind the square root of 3. Now we don't have 52 on the outside. We actually have 5 times 2. Actually call it negative 5 times 2. So that's going to give you negative 10 root 3. This is also a square root problem, so we're looking for a perfect square inside of 18. I hope you see the number 9. There's also a 2 left over, but it's the 9 that's able to come out. You're also going to take out all of this m squared. That's because it's already a perfect square. So when the 9 comes out, it turns into a 3. When the m squared comes out, it turns into an m. It leaves behind just a 2. Okay, there's no m left behind because all of that m squared was taken out. How about the product property? It's really the same thing that we've been doing. It's just that you're able to really split this into and think about taking out for each of these items. Now, for 32, it would be advisable to split that into not 8 times 4, okay, not 8, but 16 times 2. Why do I want to use 16? Well, this is a fourth root. Since a fourth root, I need a number that's has a perfect fourth power. 16 is the same as 2 to the fourth power. So I want to be using 16 as my number that's going to come out. Let's take it out because 16 is going to turn into a 2 when it comes out. It is going to leave behind this 2. Let me fix up my colors here. So 16 turns into 2 when I take that one out. Now how about this x to the 5th? Remember, you want to think about the largest amount of x that's inside here. The largest amount of x that's inside of x to the 5th that is going to work evenly with that 4. You want to go the whole way up to x to the 4th. Okay, because when you take out x to the 4th, it's going to divide, and that's going to leave us with just an x to the 1st. Normally don't write that. It also leaves behind that x. Okay, so we take out the x to the 4th because it's the highest amount that's divisible. It looks like that we have one more number here we can sort of split up. The highest amount of m that's inside of 10. The highest amount of m that's inside of 10 would be m to the 8. And you're able to take out all of that m8. You divide it, and it leaves you with m2. Again, I divide it by this 4 out front. It also leaves behind m2 that did not come out. All right, so we have, what do we have here? We have 2x m2, the fourth root of 2x m2. It's kind of interesting. We have the same thing on the inside as we end up on the outside. Now, the product rule specifically says that I can take 2 items and make them 1. It would be a good idea to make this 1 since you're able to multiply underneath here. You're able to turn this into the cube root of 8x cubed. Look, you have perfect numbers all around. I can take the 8 out. It turns into a 2. I can take the x3 out. All of it comes out. You divide by 3, and you just get x to the 1st, or just x. So our final answer is 2x. Finally, we have everybody's favorite, the quotient rule. Now, the quotient rule says that I can split this into a numerator and denominator. Of course, when I split into a numerator and denominator, I create the ever famous square root, or in this case, cube root in the denominator. You can't have a radical in a denominator, so you're going to have to multiply the top and bottom by some more denominator. How much more denominator? Well, you want to multiply by enough denominator to end up with 3. Of course, I already have 1, so I'm going to want to multiply by, by 2, okay, by x2, because that is going to give us a total of 3. You got to multiply the top by x2 also. Now, everything in the bottom is going to end up canceling out because I'm going to get the cube root of x3. Okay, the cube root of x3. So that's going to cancel, and that's going to leave us with just x in the bottom. If you want to skip to that, you can. It looks like in the top, I'm going to end up with 2x squared. Nothing changes there. So we get the cube root of 2x squared all over x. All right, here we have a fifth root of 32y5 and the fifth root of x20. Now, before you get too excited here, it turns out that everything here is able to come out evenly. Okay, do you recognize 32 as a perfect fifth power? Okay, 2 times 2 times 2 times 2 times 2 equals 32. That means that means the fifth root of 32 is going to come out right away as a 2. Now, we're also able to take out this y to the fifth because you can divide it by 5, and that, of course, just becomes y to the first power, if you'd like to write it to the first power. And how about this 20? All of that, this x20 is able to come out because you divide it by 5, and you end up with x to the fourth. So nothing needs to be rationalized. I don't have to multiply the top and bottom, which is nice. We just end up being able to cancel everything. I have a feeling that number 14, we're going to have to do some canceling, but let's get down to business. Let's split it, and let's get a third root of 4. Now, can't have the third root of 4, so you got to multiply by more 4. You got to multiply by how much more 4? How much more 4? You want to multiply by 2 more 4. That's because you already have 1 and you're trying to get 3. So we multiply by 4 squared. We multiply by 4 squared. Now, 4 squared is actually the same as 16. So when you get thinking about the numerator, by the way, the denominator just cancels to be 4. But when you get thinking about the numerator, you're going to get a 16. So you might as well change it to 16, and then you'll have that x squared. Did you see how the denominator, though, is able to cancel to just be 4? All right, looks like I got 2 more problems here. I'm going to split this, third root of 3 and third root of 5a4. Now, don't do something silly and tell me that the third root of 3 equals 1. Okay, the third root of 3 would be like 3 numbers that multiply to be 3. We don't know 3 numbers that multiply to be 3, so let that alone. You do have some a that you can take out of here. This a, at least there's 3 that I can take out. That it does leave behind 1, but I'm able to take out a3, and when I take out a3, of course it turns into a. That's because you divide. Now, there's still some stuff to worry about underneath here. Well, don't worry about it. Let's deal with it. You see, you can't have this root of 5a, so we're going to have to multiply by more denominator. We're going to have to multiply by how much more? Okay, well, we want to end up with a total of 3. Each of these is just counted once, so we're going to have to multiply by 2 more. That means up here in the numerator, I'm going to also multiply by 5 squared and a squared. Okay, now, what happens in the denominator? Okay, well, what happens, first of all, is that this blue a just carries through. Okay, the blue a carries through, so I'm going to write it down again. But all of this stuff we did here is going to cancel to just be 5a. Okay, that's because we end up being able to cancel the 3's. So if you look at your denominator carefully, you can see that you're going to end up with 5a squared. Now your numerator, it's got this 5 squared, which is the same as 25. And 25 is going to get multiplied to this 3 that's been hanging out here. So that's how we're going to end up with 75. Again, I get 25. It's going to multiply to this 3. And that leaves us with 25. How about the a squared that was underneath here? That's still underneath. Okay, so we get the cube root of 75a squared over 5a squared. That is not an easy problem. Okay, but I'm giving it to you as a challenge, and giving you an opportunity to try to learn a harder problem. Now, number 16 is really the same idea. I encourage you to follow the same steps, and you end up ultimately with an answer of the cube root of 36x squared all over 3x squared. Okay, it's a similar problem where you're going to have multiple steps before you end up with that final answer. It's the cube root of 36x squared all over 3x squared.